Okay, so we're going to continue with differential equations, and now I'm talking about Euler's approximation method. Okay, I don't know if you remember the many videos ago in this calculus course of mine. Well, it's not. Yeah, it's a calculus course of mine, but it's not my book. I'm using somebody else's book to teach this. I taught a Newton's approximation method to find out the roots, right? So if you had something like this and some kind of function like that, maybe from here you were gonna get the slope, and then it would come from this part of the function. You were gonna follow the slope because the slope can go this way or it can go down, but it was gonna go down all the way to y is equal to 0, right? I don't know if you remember that it was like you're trying to find out the x of the root, so that was going to be like x equals x0 minus f of x0 divided by the first derivative f of x0. You were going to find x1, and then here we're going to do the same thing. X2 equals x1 minus f of x1 divided by the derivative f of x1, right? You were going to do these things. Well, there's also Euler's approximation method to find out the solution of a differential equation. What is a differential equation? I already taught you guys what it is. But the solution is to find the y. Okay, so if you have like the third derivative minus 5 and the second derivative plus 6 and the first derivative minus 7y equals 0, for example, or equals some kind of constant like 17. Okay, the solution of this differential equation is to find this y. You have the differential equation, but you don't have the equation. You don't have this yet. That's what you're trying to find out, all right? So Euler's approximation method, again, it's not perfect. It's just an approximation method to find the solution for the equation, for the y, because you don't have the y. But you're going to start with an initial point like x0, y0, and from here you're going to get an x1 and a y1, and from here you're going to get an x2 and a y2. So you're not going to get this equation, but you're going to get all the points that are close to the equation. How close? It depends on the step. Okay, what is the step? The step is h1. As a matter of fact, h1 equals x0 plus the step that we call h. So it's x1 equals x0 plus the step. Okay, the smaller the step, the closer the x's are going to be, the points they're going to be. Okay, instead of just being one point here and then another point here and another point here. No, it's going to be one point here and another one here and another one here and maybe another one here and here and here and here and here. And you can see that the x distance between one and the other is very small. Okay, it's always the same. That's the step. So how do you find this stuff? Okay, well, here you go. The xi is going to be equal to, you're going to start from x0, right? But xi is going to be xi minus 1 plus h. Okay, and the yi is going to be equal to yi minus 1 plus the h times the derivative of the function. Okay, at what point? At the point that you already have, which is going to be x minus xi minus 1 yi minus 1. So you go like, what does this mean? Okay, for example, let's just say that you get a function like this. This is the real function, and but you don't know that yet. You don't know this, okay? You're trying to approximate that stuff. So you start from here. So in here, let's just, I'm going to exaggerate this step on purpose to make it easy, because if I make it extremely close, you can even see it. So I'm going to exaggerate the step like this. Okay, so it's going to be this is x0, y0. You have to start with a point that you know that belongs to the function. You have to know, the exercise has to give this to you. Okay, this point has to be on the function. And now from here, you're gonna get the slope, which I think, oh man, I think it's kind of like that. Maybe in here, kind of like that. Okay, so I'm gonna have a step from here like all the way to here. Okay, so using this slope, do I know that the next point is here? No, I don't. This is gonna be the step. Okay, so kind of like in here, this distance is h. So this is x0 and this is gonna be x1. So x0 plus h, x1. Okay, fine. How do I know what the y1 is? Well, the y1 is just going to be this approximation here. This thing means from this is going to be the yi minus 1, okay? The y0, and I'm going to get the y1 by following this slope. Because it's the closest that I can get. I can follow the slope all the way up to here. Now this is going to be my new x1, y1. All right. Now here's the thing. This point right here was part of the slope. Okay. So how am I going to do this? I'm going to do this like x1 equals x0 plus h. y1 equals y0 plus h. And this, the function, right? The derivative of the function. Do you have this derivative of the function? Yes, you do. You have to be given this stuff because you don't have f. You don't have f. F is what you're trying to find out, but you're not going to find it. So if you don't have f, how are you going to get to this graph in here? Okay, you have to get it by point, making the computer do the approximation for you. And this is the algorithm. This is how the computer will be programmed. So you don't have f, but you have f prime. Okay. And this f prime has to depend on x and on y. So this is going to be x0, y0. So now you have x1 and you have y1. And you're probably thinking, okay, so how do I find x2? Let's do it. x2 is going to be x1 plus h. What about y2? y2 is going to be equal to y1 plus h times the derivative of x1. Okay, I'm going to make a real one here. 1, okay, y1. And now somebody's going to think, okay, but there's something wrong here. Because this is the formula of the derivative of the slope at x0, y0. And the graph goes through x0, y0. But what about x1, y1? x1, y1 is this point here. The graph doesn't go through it. I know. That's why the steps have to be small. Okay? Because it's just an approximation. So, whoever made this method, which is Euler, he just thought, okay, if the step is small enough, okay, if the step, I'm just making this exaggerated step in here for it to be visually easy for you to see. But the step is not going to be this large. The step is going to be something like this. Something very small, maybe even half than that, like that. It's a little tiny thing, okay? What did Euler think when doing this? He thought, okay, the slope from this, if the step is small, the slope in here, this point, the true slope, is not going to be very different from a slope that is passing through a point close to the real point. This is the approximation point. This is the real point. But since the points are too close to each other because the step is small, then the slopes are probably not going to be too different from each other. Okay? That is the assumption of this algorithm. So that's how it works, guys. And you see, you're gonna see that this is actually the point slope equation, all right? Because it's like this is what you're trying to find out, okay? So you can see that this is like y equals y0, which is the point that you have, plus, remember that point slope equation of the straight line that you have in m, which is the slope, okay? And then you have x minus x0. Well, this y here that you're trying to find out is this one. This y0, which is what you have, is this one. The slope is here, okay? And the x minus x0 is actually going to be in here. It's the step, okay? The x is what you're trying to get. But this is going to be very easy to find out because the step is always the same. So x1 is equal to x0 plus h. x43 equals x42 plus h. x2 equals x1 plus h. You determine the h. How am I going to know what the h is? You determine it. But the smaller the h, the more precise you're going to be in the algorithm, in the approximation algorithm. The downside is that you're going to have more, right? It's linearly inversely proportional. So if the step is half to get from point A to point B, you're gonna need 2 steps. If it's a quarter, you're gonna need 4 steps. If it's 1 divided by 16, you're gonna need 16 steps. So the smaller the h, the more precise you have, but the more computations the computer is gonna have to do for you. So that's the general idea, okay? And now I'm just gonna show you some proprietary content, right, of the book that I'm using. I didn't create this stuff, guys. This comes from somebody else. Okay, so I'm gonna show you here. Here you go. So see, this is the initial point, and then you add the step, and you use the slope from here to find out where the next step, where the next y is going to be. And then you find the slope in here. Even though the real function doesn't go through this point, you're going to find out the f of x1, y1, and the slope is this one, and then you're going to add another step. And according to this slope, you're going to come up all the way up here. And now you're going to do the f of x2, y2. You're going to find out that the step is coming over here. Okay, the slope comes here. So adding another step, you're going to go way up there. So you can see that this is the approximation and this is the exact curve. Okay. And I'm going to show you some stuff in here. Like, first I'm going to erase this. Okay. Let's do that. Okay. So use Euler's method to approximate a particular solution of the differential equation, blah, 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 blah. Passing through the point 0, 1. Use a step of 0.1. Okay. So y1, so what is going to be the initial step? The initial step, y1, x1, well, okay. Let's go. Y1 is equal to y0, h, which is 0.1 is the step, times f of x0, y0. Now, what is x0, y0? 0, 1. So it's going to be 0 minus 1, that's minus 1. So you have 0 minus 1 in here. That's going to be 1 plus minus 0.1. So it's 1 minus 0.1, which is 0.9. And now you have the y1 and the x1. What is the x1? Well, it's 0 plus the step. So it's 0.1. Okay. So you can see that this is always going to be the x1 minus x0, x2 minus x1, x3 minus x2. So you see 0, 0.1, 0.2. And now you find the y1. So the y1 is going to be over here to find y2. And the y2, which is 0.82, is going to be used over here to find y3, and you keep going. Now, following this, right, this is where you're going to find, yeah, it actually gets pretty close, right? So you see that? The exact solution is the gray one, and the approximate solution is this black one right here, using a step of 0.1, okay? If the step is even closer, like 0.01, you're going to be way closer, but you're going to have 10 times as many steps to get from 0, x equal to 0 here, to x equal to 1 here, okay? And let me see if I'm going to be done with this video. Yeah, there's something else that I want to show. It's just a table, right? This is a table of the values using this thing, okay? So the first x and y are 0 and 1, the second one is 0.1, 0.9, the second one is 0.2, 0.8, 820, right? And here's the end. So in 10 steps, you got all these points, and using all these points, you plot this black curve in here. The computer is going to plot that stuff for you, okay? And the exact solution is this one. So it does get pretty close. Of course, you're not going to be doing this by hand. I'm just teaching you this algorithms, Euler's approximation algorithm, so later in life you can program a computer to do that for you, but all of this is automated. Okay guys, that'll be it for this video. Thanks.